So now we've seen all the different examples with concave mirrors, okay? But before we go any further, we should talk about the few basic rules just to recap everything that we've seen, okay? Aside from ray tracing, you have to understand a few basic rules about concave mirrors. And by the way, this only applies to concave mirrors. Rule number 1, we know that when the object is placed behind the focal point, it's going to produce a real image. So that means it's going to be upside down, okay? But when the object is placed in front of the focal point, it produces a virtual image, which is right side up. And we see that, of course, with our example over here, okay? When the object is behind the focal point, in this case, we can see where the focal point is, then the image is going to be real inverted. But when the object is in front of the focal point, we can see that it's going to be virtual and upright. Rule number 2, the size of the image, which I'm going to say HI, height of the image, okay, is directly proportional to the distance of the image from the mirror. Meaning that if you have a larger image, it's literally farther away from the mirror. Whether this is real or virtual, this both holds true. So we can see over here, okay, as the virtual image is getting larger and larger and larger, it's getting further and further and further away. In this case, same thing with the real image. With the real image, as the real image, which is upside down, gets further away, it gets larger and larger as well. And you guys may have noticed one other thing. The fact is, the closer the image is, the closer the object is to the focal point, the larger the image is. So overall, as you see that candle over here, as it moves further away from F, the image is getting smaller and smaller and smaller, but as it moves towards F, it gets larger and larger and larger. That break-even point is right at C, where the object and image are the exact same size. But basically, between C and F, the image is larger and larger and larger and larger, until at F, of course, there's no image whatsoever. When you move in front of the focal point, you create a larger and larger image the closer you are to F. So having it as close as possible to the mirror does not make a large image. You have to have it close to the focal point of the mirror to create as large an image as possible. And now we're going to move on to convex mirrors, about ray tracing convex mirrors and the rules that apply with convex mirrors. Okay, so all those rules that we just wrote down for concave mirrors don't apply to convex mirrors. But it's okay, because convex mirrors are very straightforward. They only have one rule. And the one rule that they have is that they only produce smaller virtual images. Okay, I mean, think about the security mirror, right? The security mirror in the store or in the locker room. Whenever you look at yourself in the security mirror, you always see a smaller version of yourself. But what gives you the opportunity to do is also see all the surrounding area around you. So convex mirrors are great to see in further places, and we'll see that with our example on YouTube right over here, where we have a golf pro
so that they go like this, and they don't go like this, and then they stop, and my arms go. I don't want to go like this, and then over. And I can see that in the mirror. That's a big deal. The other thing would be...
So if this is a regular flat mirror, he would not have the opportunity to see his entire body. He probably only see his legs up to a certain point. But because it is curved, he can see much more around him. But notice, the image of the person is smaller and is upright, which means that it is virtual. We also see convex mirrors in cars with side view mirrors and with the rear view mirror. Have you ever noticed that the side view mirror always says, as you see in the comic, objects in mirror are closer than they appear? That's because the mirror is curved. So that way it gives you a wider point of view when you're trying to look behind the car. And the thing is, when it gives you a wider point of view, it's generating a virtual smaller image. And your brain thinking that because it's smaller, it might be further away. When in reality, as they say in the mirror, objects in the mirror are closer than they appear. Okay? And as you guys can see, there's a giant eye in the mirror. Now, when we talk about ray tracing a convex mirror, it gets to be slightly more complicated. Because you guys may have noticed, the focal point is behind the mirror. So when we have the focal point behind the mirror, well, light can't go through a mirror. But we still follow the same exact rules. Okay, we're still going to follow the same ray tracing rules of parallel to through F. Well, let's do that right now. Parallel. That's not parallel, but it's close enough. Now, the thing is, when it hits the mirror, it's actually going to reflect off the mirror as a diverging mirror would. It reflects off. But because it's still pointed at the focal point behind it, if you bring back the virtual line, it passes through F. Okay, normally you guys would use a ruler, so it'd be a lot neater. The second line, normally we do is through F and parallel, but for convex mirrors, it's a little complicated. So rather, I'm going to use the third line, one of my check lines, straight through C. But C's on the other side. Yes, I know. Well, that means when it hits the mirror, in reality, it bounces back. Well, straight exactly on the point, okay? But if I bring it back through, it passes through C. And where those two lines converge, there's my virtual smaller image. Okay? And the fact is, that's the only type of ray tracing you have to do because the focal point is always going to be on the other side. Even if you move the object further back, like in this example over here, the fact is that it's still going to be parallel, backtrack through F, virtual through F, and then straight through C. And you have a virtual smaller image. There's no location you can draw where you have no image, like with a concave mirror. A convex mirror will always produce a virtual smaller image. Concave mirrors can produce virtual or real, but a concave mirror will produce a virtual larger, while a convex mirror will produce a virtual smaller image. Okay. Now let's talk a little bit about the math behind drawing for mirrors. Okay. And the fact is, when you do your math should match up exactly the same way as your drawing does. The mirror equation that we're going to use is 1 over di, distance of the image, plus 1 over do, distance of the object, equals to 1 over f. I know it says SI and SO. I just prefer DI and DO myself. Okay, distance of the object, distance of the image, and F, of course, is the focal point. But the most important thing to remember about all these things is that they are always measured from the mirror itself. Okay? Now, it's positive when it's going to be real, and negative when it's going to be virtual. Okay? That applies to all of them. The object, the image, and the focal point. So, for example, with a convex mirror, right, the security mirror, if we draw a quick sketch of the convex mirror, there's F, there's C, there's the object. Okay? Everything where the eye is, that's always going to be real. Okay? Wherever the eye is, that's where the rays of light really are. That's where the person really is. Over here, we have the negative side where we had traced out our virtual lines to create our image. And the focal point is also on the negative side, the virtual focal point. So that means when you do your math, okay, your f is going to be negative, and your di, when you calculate it, should end up negative as well, while your do would be positive. And because the size of the image is always being changed, we have to talk about the magnification. Magnification is simply a ratio. How big the image is as compared to how big the object is. So it's very straightforward, where it's a ratio between the image and the object. Okay? But remember, as I said before, the image size is directly related to the image distance, meaning the larger it is, the farther away it is from the mirror. The smaller it is, the vice versa. So we can also write out negative di over do. And the negative sign is there just to help you understand when it's going to be a real image or a virtual image. Because if m is positive, that means it's upright. If m is negative, that means the image is actually upside down or inverted. And of course, upright means virtual, and inverted means real. We can combine our two formulas together just to solve for hi itself. If you cross multiply, hi ultimately equals to negative distance of the image times height of the object divided by distance of the object itself. But in reality, it's just the ratio of the distance of the image to the distance object times the height of the object. So if we do a quick example question with this, okay. A 1.5 centimeter high diamond ring is placed 20 centimeters from a concave mirror whose radius of curvature is 30 centimeters. Okay, determine the position of the image, the size, and whether the image is upright or inverted. Okay, so let's actually copy this onto our smartboard. Okay, so here's our problem. Okay, you should label where it's positive, where it's negative. Positive is where the eye is. Negative will be the virtual side. We'll label our focal point. We'll label our center. They even give us some nice numbers here to use. And they say the object, for example, is placed 20 centimeters from the concave mirror. Now, whenever you do a problem, you should try to draw it first if you have the opportunity to do so. Okay? Then, when you do your math should match up with your drawing. So in this case, we can see that the object is behind the focal point. It's behind the focal point, and it's going to produce a real image. But it's close to the focal point, so that means the image is going to be larger. So it's going to be a larger upside-down image. Let's see if that works out. We have parallel, then through F. I know I missed it just a little bit. And the second line is through F and parallel. Okay. Now, I know this is a terrible drawing, but we can see that overall it's going to match up somewhere back over there. Okay? And when it meets up, it's going to produce a larger image. Okay, fine. Let's see how this works out mathematically then. They tell us, aside from the fact that the object is placed 20 centimeters away from the mirror, they also say that the radius of curvature is 30 centimeters. If the radius is 30 centimeters, well, we should automatically know that the focal point is half the radius, so it equals to 15 centimeters. Okay? And they also tell us that the diamond ring is 1.5 centimeters high. So they're telling us that the height of the object is 1.5 centimeters. Okay. And now taking all this information, okay, we should understand that with DO being 20, with F equaling to 15, we should be able to solve for the distance of the image from the mirror right away. We just use 1 over DI plus 1 over DO equals to 1 over F. In this case, I know it's a positive focal point because it's on the positive side. So if I plug this in and solve for DI, 1 over DI is equal to 1 over F, 1 over 15 centimeters. DO, I would have brought to the other side by minusing it, minus 1 over 20 centimeters. Okay? So you can use your calculator if you want, but let's just find the common denominator here, which is, of course, 60. So this would be 4 over 60 minus 3 over 60, which equals to 1 over 60 centimeters. But I don't want 1 over 60 because I'm not looking for 1 over DI. I'm looking for DI. So if I flip both sides, I end up with DI is equal to 60 centimeters, which is approximately what we saw. The fact is the image is much further away. It's a positive distance, which means that it is real, which is matched up with our drawing as well. And now if we solve for the height of the image itself, height of the image over height of the object is equal to distance of the image over distance of the object. And I know I'm running a little bit out of room here, so let's move this onto another page. High over ho equals negative di over do. Okay? So if we cross multiply it, we'll see that the height of the image is equal to negative times distance of the image, which was 60 centimeters, times height of the object, which is 1.5 centimeters, divided by the distance of the object, which is 20 centimeters. Notice that the distance of the image to the object is a ratio of 3. It's 3 times further away, which means that, of course, our image is 3 times larger. But it's negative because it's upside down, it's inverted. Okay? So when you guys do your own math problems later on, make sure you always label what's positive, what's negative by looking at the drawing first. Label the positive side, label the negative virtual side, and make sure you label everything correctly. Okay? And we are done with mirrors.